In regression, we always tend to assume we just observe the world around us, we collect data, and then run our regression. In experimental design, we deliberately try to choose values for the x-axis. We do experiment with them and observe the outcome. However, the ANOVAs that we have discussed and the technique of regression still applies in the field of experimental design. It's just that the axes are deliberately manipulated. So I have now two examples stemming from experimental design, and we will think about whether there are interactions or not. Experimental design is taught in STAT 372 and also in STAT 332. First example, cut flowers. It was an experiment to find out what factors make cut flowers last longer. And specifically, we experimented with two cutting methods and two liquid solutions to be added to the water. The outcome is the number of days the flowers lasted. And just adding those two indicator variables without interactions into the model, we have here time in terms of number of days, an indicator of method 2, and liquid 2. Looking at the data, here are the data. The time is plotted on the y-axis. And really, these 2x2 combinations give us 4 points, 1, 2, 3, 4. And this is the raw data. So this is just the average of all the cut flowers in that combination of experimental condition, right? In one of those 4 conditions. And so the intermediate values don't exist, right? Condition 1, condition 2, but we can still draw lines. So what does the graph suggest in terms of interactions? I will leave you to answer that question and move on to the next example. Second experimental design example in advertising. An advertising firm wants to see whether two features, color and image, affect sales. And they experimented with 3 colors and 2 images. Just adding indicator variables without interactions. The model is sales as a function of indicator for image 2. And then for colors, we have 3 colors, so we need 2 indicators for color 2 and color 3. Again, we can plot, this gives us 6 experimental conditions, right? 2 times 3, which leads to 6 points, 1, 2, 3, 4, 5, 6. We can plot the data and connect them. And the question is, again, does this suggest anything, now it's a little more complicated, about presence of interactions or likely presence of interactions? So I leave you to answer that. Moving on, same setup, different graph, still 6 points, and similar questions, similar answers. And I will leave you to answer that again. So far, we've talked about interactions between 2 indicator variables and 1 indicator variable and a continuous variable. There's no reason why you couldn't have 2 continuous variables. You just multiply them together, you have an interaction. The reason why that's not all that common is because interpretation is much, much harder. Right? For when you have 1 continuous variable, then you're just getting a different slope for the other level of the indicator variable. If you have 2 indicator variables, instead of making a general statement of 1 indicator adds something or subtracts something and the other one does something, instead of making these 2 separate statements, you just say, well, we have 4 different points. These are the averages, or the model-based averages. But no such interpretation exists for 2 continuous variables, and that's why it's usually not included. Occasionally, you might include it to improve model fit, increase R-squared. Interpretation is tough. All right, that concludes this segment.